divide and conquer. Divide and conquer. That you have to divide, as we already learned in merge sort. Yeah, divide the input size is too. If the input size is too large, it's too big to fit to your memory, then just divide it. Yeah, it is too large to deal with in what? In straightforward manner. If by straightforward manner it is easy, okay, it means that problem is not worth it to use divide and conquer in the dynamic programming. Yeah? Divide and conquer is only for so-called complicated problem. If this by straightforward manner, it can be solved, then for what? Let's just use that simplest one. Okay, so if the input size is too large, then divide the problem into two or more disjoint sub-problem. At least two, like we discussed, the binary search tree can achieve log n. Merge sort also divide at least two, can achieve n log n. And then conquer. What is conquer? Use divide and conquer recursively. That this can be used recursively. Okay, to solve the sub problem, because remember this divide by 2, yeah, and then there's the children also can divide by another 2, so it means totally 4. Totally 4. So that means this principle can be used for the descendant problems, also call it sub problems. But after we divide that original problem into sub problem, also come another one that we have to combine, so that the original problem where temporarily you solve that sub problem, then we have to combine it, that so-called sub solution, yeah, to get back to that sub original solution from original problem. So this combine, take the solution to the sub problems and merge. Remember that merge sort, yeah. So until the very end, let's say until the leaf, yeah, until the leaf, yeah, and then you combine, go back until that original problem. Okay. So remember that merge sort, yeah. Take the solution to the sub problem and merge the solution into a solution for the original problem. Again, for example, merge sort. Okay, yeah. Actually, we already did this. I think we don't need to discuss too much about it, so to save the time. So we have array that you have P and then what? R, yeah. Then you divide by in the middle, yeah. Let's say this is Q. So you have Q in here and then Q plus 1, right? For this is by APQ and Q plus 1 until R. The sub problem are independent and all different. Okay. But you know, I think it's quite clear actually the method. But this is there's much easier example. You call it in some sense, like the easiest example is so-called Fibonacci numbers. Yeah, that if you have Fn, you have the formulation of Fibonacci number like this. Defined by Fn equal to Fn minus 1, it means the function with the previous state, yeah, n minus 1. The input before n, it means n minus 1. And also the previous one. So the current number, the current state now is equal to the previous number, previous state, plus the previous of the previous, yeah, f minus 1 plus fn minus 2. If I, because it means I have at least 2, yeah, to state this fn minus 1 and fn minus 2. It means I need 2 numbers, yeah, to get the first one, this. And then we assume that if f0 equal to 0, then f1 equal to 1, then you have, okay, number 1, 0, correct or not? Because fn, yeah, it means fn now, yeah, equal to what? Equal to fn minus 1 plus fn minus 2. Okay. Fn equal to Fn minus 1 plus Fn minus 2. So in this case, yeah, so you have F0 and F1, then you can see, so okay, F0 this 0 and then 1. Then after that, just add up this, yeah, 0 and 1 become 1, right? And then you add up 1 plus 1 become 2, right? Then so it means this 1, yeah, from 0 plus 1, right? Plus 1, yeah, plus 1 plus 1. Okay. 2, it means 1 1, yeah, 1 plus 1 2, right? And then 1 plus 2 plus become 3, right? 3 plus 5 plus 5 become 8, right? And so on, yeah. 8 plus 5 plus 8 is 13. 13. 3. 8 plus 13 is 21, and so on, yeah. 13 plus 21 is 34. Is this the Fibonacci number? Straightforward recursive procedure is slow. Really? Why? Why? How slow? Let's draw the recursion tree. Okay, see the recursion tree like this. Okay, so this is the initialization. Yeah, I mean F0 is 0, F1 is 1. Then okay, F1 this, yeah, once again, okay, 1. Then 1 plus 1, F3 become 2, so on. The thing is, as you can see here, guys, yeah, why it is so slow, this straightforward recursive procedure? Why it is so slow? Thing is, 3, yeah, F2 is F1 plus F0. The thing is, when you calculate F4, because F4 is Fn minus 1, no, n equal to what? 4, yeah, n equal to 4. It means n minus 1 be 3, yeah, n equal to n minus 2, it means F2, right? Okay, F2 it is minus 2, 1, and is n minus 2. And then actually, F2, yeah, need to calculate, yeah, from F1 and F0. Actually, this already done here, yeah, already done in here. Then once again, you need to do, and so on. Okay, when F3 already done, this F3, if you, when you calculate F5, and then you again, you need to calculate to F3 and so on, yeah. So this, we keep calculating the same value over and over. We keep calculating the same value again and again. Okay. How slow? You can imagine, yeah. As time passes, it becomes slower, yeah, because you calculate again and again much more, yeah, more processes. Yeah. So slow, very slow then, yeah. How many summations are there? How many summations are there? You have golden ratio, yeah, Fn plus 1 divided by Fn equal to this V, yeah, like 1 plus square root 5 divided by 2, 1.6 something, yeah, this. You know that golden ratio, yeah. The golden ratio can be used for many things. Golden ratio. Actually, this, for instance, golden ratio, this, yeah. That's a golden ratio. This is golden ratio actually here. I think simple one, this. This golden ratio is this. What is the ratio of A, yeah, comparing to A plus B? A to A plus B. So of course this, but the golden ratio make conversion. Yeah. So this A plus B is to A as A to B. Yeah. So A plus B to A as A to B. A to B. This is like 1.6 something. 1.6 something. Yeah. A plus B to A or A to B. It's phi, that phi. Yeah. P of phi. This is P of phi. P. P. 1.6. Actually, this can be used for many points. That Mona Lisa, yeah, the ratio. Also, the ratio for like for beautiful standard, yeah, standard beauty standard of face, also golden ratio. I think one of them is also this, yeah, this, yeah, golden ratio. Then you can just which one like the face fit the golden ratio is quite a lot. Yeah, of course, usually actress, yeah, because they're beautiful. Okay. Like to say that Amber, yeah, Amber Hot, Angelina Jolie, Jennifer Aniston. This for the female, yeah. Yeah, of course. I mean, uh, yeah, I mean their faces can be seen, yeah. Tom Hardy, that NFL player, yeah. Even Kim Kardashian, yeah. Even Madonna, Tom Cruise, and so on. And then you can see, yeah, that oh, even that's Jennifer Lawrence, yeah, and so on, yeah. Okay, Robert Pattinson, and so on, yeah. So this can be used a lot actually. That golden ratio, yeah. So thus, yeah, Fn equal to 1.6 power n. If we have Fn, how many? Yeah, I'll put on Fn, F, then 1.6 over n. Our recursion tree has only zeros and ones, right? Because we only have the basic one is 0 and 1. Okay, 0 and 1. Only zeros and ones. Must leave. Thus we have 1.6 power n summation. So running time is exponential. The thing is, yeah, if it is 1, you make you put any exponent here, yeah, any even n is okay, yeah. Of course, 1, yeah, doesn't matter. But the thing is, when 1 and then you have dot and even already have something here, even 0, 0, 0, 0, 1, yes, this thing. Okay, so it's very funny, yeah, that when it is maximum 1.0, then it's okay, yeah, or less, yeah. Of course less. For instance, the 0. Even 0.999, yeah, then it is power, yeah, power was that, let's say power 10, power 10, this is power, yeah, that had is power. Okay, where is that? So it's okay, 0.9, of course, as if it is power exponential, exponent, that exponent, yeah, the number in that power is 100, yeah, it is getting what, getting, it is decreasing 1000, yeah, yeah, because it's decreasing, okay, yeah, maximum what, maximum 1.0, yeah. If 1.0 power whatever, of course 1, yeah. But the thing is, when you put some number, even though very small, yeah, let's say 10 first, yeah. Okay, this, yeah, very small. But as time passes, okay, let's say 10,000, the n, yeah, already this already close here, and so on, yeah, because this also become very big. The, let's say if it is already like, wow, very big, yeah, already very big. Which one? Make it, okay, it's already very big. Yeah. Even this is many 1 million. 1 million is already 2.7 something, yeah. Okay, so this why it's very dangerous, because running time is exponential. Anything about sial, unlucky, yeah. Of course, as usual, the worst is something, and then you put n in here. But I mean that question mark should be anything greater than, yeah, greater than 1. Yeah. Anything greater than 1. Yeah. Because if 1 is okay, care. Yeah. If it is less, of course, even better. Yeah. If less, then decreasing it. But it's greater than 1, and then whoo, exponential. Yeah. Okay. Okay. Then we can calculate Fn in linear time by remembering solutions to the solved subproblem. That's key. So if somehow, guys, when you can remembering. It means you save some portion in this process and then you use it in the next process. Or if you think like the current process, actually you save the previous process. Call it remembering solution. Remembering solution. If you save that state, if you talk about the current process, I mean you save the previous process. Or if you talk about the future, you save it now. Then you can use in the future. Then you can call this in, because it's actually not total linear time, but close to, and we can call it linear time if we talk about asymptotic analysis. We can say that this linear time. Yeah? Calculate Fn in linear time by remembering or save it in some storage or space to the solve problem. Yeah? That's DP. That's only this. Then probably only this. Yeah, if you are save some process, actually sub processes, yeah, because we already defined to be used later. Okay. And then compute solution in a bottom-up fashion. Bottom-up, yeah, this. Because remember, if we talk about that Fibonacci, yeah, this is from the leaf, right? Then you go up, yeah, until the root. Then in this process, you save it. Okay, you save that particular state. It means when you save or remembering this, it means you need what? Temporary or additional storage, yeah, or additional space. But it is okay because what? Because we trade that space for time. We sacrifice some space in our process for reducing huge time. In this case, actually not so much for sacrificing space. Only two values need to be remembered. So you only need to remember only two, the value before and before you, before you and before you. Only this to be remembered at any time. At any time. It means if I have this, yeah, so I have to remember this two, yeah, then okay. I can have to remember this two and then to be used for next. That's it. That's it. Okay, now we have so-called optimization problem. We also can use that. Actually, we need that book, yeah, because that physical book I already put back in campus, so I only have that PDF one. Where is my PDF book? PDF one. Yeah, this, yeah. Pak Korman. Optimization problem, yeah. But actually, I also put it there. Programming is chapter 15. Should be somewhere in data structure. After that, yeah, this advanced design. Actually, yeah. Okay. Of course, many optimization problem, yeah. Okay. Okay. For instance, this problem can be used in rat cut. This rat cutting. Yeah. Mm-hmm. The first example, yeah, okay, just use this because it's also quite simple one. So yeah, this rod cutting. The thing is, you have that rod, yeah, kind of a bar, steel bar, for instance, guys. And then the thing is, only this bar, yeah, more expensive, yeah, too. This is become $5 per item. If it is that one like this, yeah. This $1, this is $1. If two, $5. Yeah. If three, so it means three like this, yeah. 3, 1, 2, 3. Yeah. It is $8. If four, it is not so much. I mean, you add additional one, but not so much. Only $9. Yeah, this like this. Yeah, here. Example like this. Yeah. And then which one? You can check which one. Okay. If 4, it is only 9. If 1 and 3, also 9. I mean the combination, right? If 2 and 2, it is 10. If 3 and 1, it is 9. It's 10 so far. If 1, 1 and 2, only even 7. If 1 and 2 and 1, even also 7. If 2 and 1, 1, also 7. If 1, 1, 1, 1, even only 4. You can guess, so this is the C. Maximum one is C, right? It's the best. Okay, this is the best. Okay. Yeah, this is also so-called, what to say, the optimization problem, We have to choose one solution out of many. One with the optimal. It can be minimum or maximum. With like value, of course, maximum. If cost, mean value, it means profit or benefit will be maximum. If cost, will be minimum. Okay. The solution exhibit shows, the solution shows a structure like this. It consists of a string of choices. This mean what is? It means combinatorial. This string of choices that were made. What choices have to be made to arrive at an optimal solution? The algorithms compute the optimal value plus, if needed, the optimal solution. There's two things, So optimal value, if we go back to this, optimal value is 10. What is that? View page display continues. So optimal value is 10, right? 10. So optimal value. Usually this will be obtained first, or people eager to get is the optimal value. So the value first, the 10. So as long as you come up with 10 in this particular case, okay, well, you are happy. But sometimes sometimes the optimal solution, it is that step by step. What is the process? What is the process? This is optimal value, value. It means the also like kind of result, then the result or the final result. Oh, I got 10. Okay, that's it. And then if needed, it means sometimes we have one. In this case, that if I not 10, but I know actually the process if you combine these two with two by somehow. Not one by one plus, and then okay, you combine one and then with two. Actually the same, right? But no, it is different. It's 1. Okay. So there are two things, the how to say, like the metric first of value, and then sometimes people also asking about the how to get that value. Okay. So here we'll back in here, Okay, so when developing dynamic programming algorithm, we follow the sequence of 4 steps. Number 1, you need to characterize the structure of an optimal solution. Okay. Like this, if it is straightforward, we can get result right away. It is not worth it to use that so-called dynamic programming. But if the structure of optimal solution can be obtained right away by straightforward manner, itu how to say, need to divide like method. Okay, that's it. Okay, the structure can be divided by something much smaller. Then okay, it is worth it to have DP, then programming, as our vehicle to get our destination. Then this is a structure that you can, how to say, cannot straightforward manner to solve the problem, and you see that actually there is so-called sub. This second one, the recursively define the value of an optimal. Remember that Fibonacci number, Oh, so I can recursively two. And then after that, after you get recursive, like, remember also make short of that Fibonacci number. Then you can compute one of in the bottom of Fibonacci. Again, oh, this is can do and this because the leaf is actually 0 and 1. then I can make use this. So go up until that root. So actually this tree is enough in our real life, yeah, that okay, you already got that optimal value, yeah, optimal value by analyzing what kind of structure of that optimal solution, and then actually you able to use that recurrent, yeah, the recursive. So this optimal value is, okay. And then if necessary, you can get this construct an optimal solution from computed information because you already did it, yeah. So the way you got that optimal value, guys, and then of course you can reconstruct, yeah. Then it is optimal solution. It means step by step by step, that you got that optimal value. Of course, easy, yeah. It's optimal solution. This is the process. You can call it, of course, all actually process, yeah. But this is called like this value, like the result, the final result that people eager to use, and this is the process. Who's that? The guy in our politics, I mean, politics is something very stupid, yeah. I don't care about the that in sport, yeah, in sport. Oh, that what's that? In it is in our football association, yeah, PSSI that. Oh, Indonesia is all result stupid. I don't care about the process. The most important is the result. The result is that is like Sintayong, yeah, Sintayong, that our Korean coach. Some people blaming or berating him because the result in EFF, yeah, Asian Football Federation Club, we got beating by what's that? Thailand, Thailand, yeah, Thailand. But remember this, yeah. Okay, result is important, yes. But sometimes even people, if you can also want to reconstruct to see the process. See, yeah, this construct optimal solution from computed information. Yeah, this, yeah. So this is 1 until 3, the 3, and this is the 4. Okay, actually remember this is from the book actually, yeah. From this book. Sometimes I need to refer to the book. Okay, yeah. Okay, another example is multiplying matrices, matrix. Remember, yeah, two matrices A, let's say A 2 times 3, yeah, and then you can multiply by metric B, who this is like 3, let's say 3 times 5, yeah. So the requirement is should be the same, guys, yeah, should be the same, this 3 and 3, and then the result become what, 2 times 5, yeah. Let's say this is matrix C, matrix C, right? Yeah, so n times m matrix and b is m times k matrix can be multiplied to get c with the dimension this, yeah, correct, yeah. So this will be the same, n and m, and then the result of the product is n times k, and using n mk scalar multiplication, yeah. You already know this, I mean, we could discuss this row time column, yeah, row column, yeah, and then you will got this Cij equal to sigma ai 1 dot times, yeah, b1 bl, this is bl, yeah, this l I comma L times B L comma J, where L well, from 1 until M, because it is an MK scalar. The problem is compute a product of many matrices efficiently. If only two, who cares? I mean, but the thing is, you have series of matrices. And how to get the minimum time, to get it done, if you have many matrices? Remember, multiplication is associative. Yeah, if you have ABC, I mean 3 matrices, then you can multiply AB first, and then the result of A times B, you multiply by C, or BC first, and then you multiply by A and B. The parenthesis matters. I mean, which one have to be done first matters. I mean, this why this parenthesis, I mean, it should be first. I mean, A times B, yeah. So A and B need to be multiplied first. In this case, B and C need to be multiplied first before multiplied by A. Okay. So this parentization matters. Consider this A times B times C times D, where A is 30 times 1, B 1 times 40, C 40 times 10, D 10 times 25. You can see the cost. A with B, so 30 and 40, this. So AP first, you got 1,200, I mean the cost. Then after that, the product of AP, you can multiply by C. Then you have huge, yeah, 12,000. Then okay, the product of that thing, yeah, let's say this is X times C. Then you will got D, and then you have 7,500. Total, you have 20,700. It's not that bad because the worst one you got 41,200. When this one, the worst is this. A times B, okay, 1,200. CD, you got 10,000. But when you multiply A, B, and CD, I mean the product, woo, 30,000. So it is whooping. And then the final cost is 41,000. But if you are very smart, guys, and then I don't want it, I want to multiply BC first, and then only 400. And then BC times 3, 250. Then A plus, let's say this is all Y, yeah, only 750. Total 1,400. It is huge difference, yeah. So this is the correct one. This is the stupid one. And this huge difference, 1,400 for 41,200. 1,400. 1,200, yeah. Right? How many times? Or let's say, mean only 3.4%. Yeah. The 3.4%. Okay, so we time by only 3.4%. It's amazing that if we can choose the correct, what's it, the correct order of multiplication, right? Then you can only need 3% of that stupid one, the 41,200. Only 3%. Amazing this. It is really amazing. You can imagine if it is a game, then you need to calculate because usually game have many matrices. Many matrices. Many game usually use that graphic. So many. So 3% is huge impact. Yeah? This is why we need to optimally parenthesis this. Parenthesis this. A1 times A2 and so on until n, where AI is D minus 1 times DI matrix. Let Mij be the minimum number of multiplication necessary to compute. This is the product, yeah, product. AK from K from I until J. Minimum number of multiplication necessary. So what is our observation here? The outermost parenthesis partition the chain matrix I, comma J at some K, then IKJ, it's like this, yeah. So you have I and then J, and you have K in here in between. That's why here. So the last one this, yeah, and then here you can put in here, yeah. You can check, yes, AI until AK, yeah, and then it's like merge short, remember, and then K plus 1 until AJ. Okay, and then you can guess, oh yeah, it is similar with merge short, yeah, that if I can find the minimum number of that sub, yeah, what is it, like sub item, it is similar then. Because anyway, we want to find this, yeah, which one minimum one? This, yeah, 250 is minimum. This also minimum. This also minimum. Totally, of course, minimum, yeah, right? Because you won't, yeah, you will not choose that 30,000. So stupid, man, right? That's why if all, yeah, this the minimum number, yeah, minimum number multiplication, it means you can find, yeah, this in that particular it also will be minimum at the end of the day, right? Okay. So this optimal parenthesization of matrices Ij has optimal parenthesations of on either side of K. I mean, I mean here the left side, yeah, also right side, this side and this side. Yeah. So okay, the set of K for matrices Ik and K plus 1 comma J. Yeah, remember this. You remember that merge sort and so on. So I, this is J. We have K in here. So in here, this and then K from K plus 1 until J. We also should optimum. Optimal means minimum. We try out all possible K. Yeah, this combinatorial problem. Yeah, usually DP is combinatorial problem like that. Rod, yeah, that rod cutting, yeah, rod cutting. Yeah, you can check this. Yeah, this is also combinatorial, right? You have to try. Yeah, but of course, if it is random, try. We don't need to cut. It's stupid. We try all possible K recurrence like this. Yeah, so MII if it's only one, of course nothing. Yeah, I mean if not one, of course nothing, zero. Yeah. But in MI comma J, if you have at least two, yeah. So you need to find the minimum, yeah, of this I less than or equal to K less than J. Remember, not less than or equal in this case. No, yeah. This is no. Because you need at least two. Yeah, if only one, why should? Yeah. Minimum of what? This again, yeah. Okay, again, I will. This is I, this is J, this is K in here. Yeah. It is by this, yeah. MIK plus MK plus 1, comma J, and then D minus 1 DKJ. Is the last one. Second here. This, yeah. And this, yeah. So D minus 1 plus DI matrix. Yeah, where AI is this until N, yeah. And then this, yeah, we have so-called DI minus 1 DKJ. Okay. Yeah. It makes sense, like, yeah, makes sense, right? That you need to find, yeah, this, the minimum one, yeah, like, we have this. Yeah. Because for sure, if you got in suboptimal minimum, yeah, then at the end of the day, you will get the minimum one. Yeah. Remember this A1, A2 until the end, where AI is the minus 1 plus the I metric. Yeah, this, then this, yeah, 30 times 1 times 40, and so on. Okay, this I minus 1 plus the I metric. Then it is I 10. Then the before, yeah, before. This is the index. Okay. Okay. And then the thing is, when a direct recursive implementation is exponential, there is a lot of duplicated work. Why? Can you imagine? Yeah. Actually, not all. Yeah, this is not all. Obviously, not all of the thing we need to try. Yeah, and it is correct when the direct recursive implementation is exponential. It is not you try all. Yeah, yeah. Because the thing is, right, guys? A1, yeah. You cannot multiply by this. Yeah? No, the thing is only the adjacent, right? The adjacent point, and this and all this is first. Yeah, this is why it is not, obviously not all possible. This is why that recursive implementation will be very massive uh, time needed because a lot of duplicated work. Yes, yeah. Okay. Again and again, yeah. You to try this. Okay. You have to like thinking what's going on if recursively, yeah. Okay. Because the thing is, uh, we only when it is metric, yeah. Remember, we only choose what in any particular time only two, yeah. A time B, C time D, B time C. Yeah. That's why we choose what actually we choose only N over two. Yeah. Yeah. We choose two over N. Yeah. Yeah. So in all time this only we only choose two. Yeah. Okay. Not, yeah. And then plus N. Yeah, plus N. the last one. Mean big data n power 2, yeah, n square. Different subproblem. Ij, where 1 less than, so I should be at least 1, yeah, then j less than n. This, remember this, yeah, this, and then this is the n1. This is I until j. Then you have k, for instance, in here, yeah. Okay. So it's only n, yeah, this, there are only n or 2, so what is called this? Chosen, how to say, choose from n, choose to from n. Oh yeah, your connection, what is that? Combination, yeah, of course, this combination like this, yeah. Combination this, yeah. We call it binomial coefficient. N of n, you choose k. Yeah. Binomial coefficient. We also can say, how to say, yeah, there's also many things they can be used. This, yeah. Actually, this, yeah, n is n and then k equal to n factorial divided by k if it is 2, yeah, because remember the multiplication only need, we cannot this matrix and then multiply by the other one. No, it's only adjacent, only next to you, next to you. It's why k only 2, yeah. So n factorial divided by 2 factorial times n 2. Okay. Well, this binomial coefficient. Okay. We also can say choose, yeah, that you choose k of n. So thus it requires only big data n square space to store the optimal cost. So if you have, what to say, let's say 5, yeah, 5, 1, 2, 3, 4, 5, n equal to 5, 5. Then you have to store n square, I mean 25. Okay. So big data n square space to store the optimal cost mij for each of the sub problem. Half of 2D array m until 1, m 1 until n, 1 by until n. You have two dimensional array, yeah. Dimensional array, because you deal with this multiplication, yeah. So called matrix change order di 0 until the end is for I from 1 to n. Okay. Then for initialization, so mii 0. I mean, you cannot multiply by yourself, right? Anyway. Then again, for L equal to 2 until n. So this is the next n. Then divide by this 2. For 1 until n minus 1 plus 1. Then this, I plus L minus 1 j. Then this you to put the infinite first, yeah, for mij. Then okay, yeah, q this. Then we'll cut q for mij and k cij and mc. Okay, after execution m1 comma n contains the value of the optimal solution, and c contains optimal subdivision choices of k. You can choose okay, like k, which one? 2 or 7 or 10 or whatever. Yeah, this is the c of any subproblem into two subproblem. A simple recursive algorithm print optimal parents Cij can be used to reconstruct an optimal parentization. Okay, yeah. Then you can run by yourself like the D, if 10, 20, 3, 5, and 30. Okay. Because you can check here, yeah. So you have okay, n it is initialization. Actually, what is one? This, yeah, this n this, and then n 2. I mean, you choose 2 over n, yeah, then you have this, yeah. So this number 1 n, and then you have n here, and then n here. So it should be n or 3. Okay, and then correct right here. It is easy to see that, yeah, it is big O n power 3. It turns out it is also big omega and 3 because the only this is the best, yeah. The best case is only this. We cannot say anything else. Yeah. Choose this, yeah. You have find and first, yeah, initialization, and then number one, and uh, this is for L, for I, and for J. From exponential time to polynomial, this okay. So after carefully thinking, it was because all of the combination, yeah. But actually it's stupid, yeah, because like I said, yeah, for instance, B and C, you cannot be, let's say, multiple by D cannot. But if you take into account your program without carefully thinking, and then of course you got exponential. But actually no, this, yeah, exponential. Yeah. It work, yes, but actually to check that it actually cannot. Yeah. But the thing is, you already grab it and want to calculate. But actually, it is not adjacent. And here you can see, carefully, yeah, yeah. That actually, for instance, this, yeah, if I have EC, or let's say the E, yeah. If now I'm in, okay, let's say I know in C. So C only can multiply D or by B before. You cannot just A multiple by D, cannot. Okay. But you want to choose this, like 3 times, yeah, let's self combine with something else, and then that something also combine to something else. This is why this, yeah, you have the combination. This is why this is N, and then N and N power 3. Actually, this is the big omega. You cannot beat this, yeah. So N power 3 is the best one we can get, for the matrix multiplication. You cannot compete. There is no better than big omega N power 3. Yeah, only this can do. Okay, so from exponential time is something like this, yeah, and let's say remove that golden, yeah, if it's something more than one, yeah, it's like this. Whoa, then two polynomial, yeah, polynomial. This form, it's good. Please check by yourself, right, guys. D10, 23, 5, and 30. Of course, it is 53. Okay, not so long, but 30 is very long. Okay. Okay, and then this the create the to say our strategy, to save our time. Okay, call it memoization. It is not memory. This memory. It's not memory. It is not memorization. This memory. There is no I. That memoization. If we still like recursion very much, because usually recursive, if carefully proceed, yeah, actually is quite, how to say, quite elegant in our programming. Somebody like recursive so much. Well, it's okay. Then we can structure our algorithm as a recursive algorithm. So this is not necessarily recursive. This multiplying matrices. But yeah, I remember even when our in oral defense, yeah, the thesis oral defense, associate, it's not necessarily recursive, even though most likely for DP, divide and conquers, if elegant programming by recursive, but it's not necessarily. So what is memoization? Also can check in Wikipedia. Memoization is an optimization technique used primarily to speed up by storing the result of expensive function call, like that Fibonacci. Remember, you always call all the time. Why don't just store it and returning the cache result when the same input occur again? Yeah. Why we do exactly the same thing if we just can simply save it, yeah, somehow, then reuse. Initialize all m element to infinite, yeah, and call lookup chain DAA C. Lookup chain is this. So initialize it actually this, but this 0 you just put that infinite. And then you call this DIJ, lookup chain DIJ. If MIJ less than infinite, then return MIJ. If it's equal, then this is 0 MIJ. Else for this from I to J minus 1. We have I and then J. Again, yeah. There's lookup chain DIK, here DIK, and then this should be K plus 1 until J. So DIK, this DIK here, IK, then DK plus 1 J. Plus this, the last one you compare. D I minus 1 DK DJ. If Q less than MIJ, then Q. So this okay to remember like that Fibonacci. Yeah. That Q, Q. Just how to say, save it, save it. Because anyway, if you use the same thing, that matrices this. For instance, in this case, AB, just save it, because maybe AB you will multiply by C right away, or you save AB and then you will use actually to calculate the result of CD. This why this the Q, I mean that Q, need to save it. This memoization, this Q. Okay, so then we back to the again that philosophy behind this, actually from page 1. This philosophy, this. In general, to apply a dynamic programming, we have to address a number of issues. Number one, you need to show that you have that optimal substructure in your problem. Optimal substructure, like that method, that if, well, actually the structure is that if I can divide this and this and this, and then, well, actually it will be interesting to see, because since like this subproblem also find in here, this also can, and so on. Also that Fibonacci, this this pattern, it can be very big triangle, you see the pattern. The always is usually the repetition, the repetition of that previous triangle, that triangle, okay. So that if you can show that like optimal structure, you have so-called suboptimal structure, or substructure of that optimal solution. Therefore, you can, so optimal substructure, and it can be deemed okay, maybe worth it to use DP, dynamic programming. DP, so DP means dynamic programming. What is that? That show optimal substructure. An optimal solution to the problem contains within it optimal solution to subproblems. If that subproblem, this solution actually can be used, that's why we can say at the end of the day that, well, that original solution actually contain many sub solution, where that solution itself should be also optimal. Okay. Optimal solution to the problem contains within it optimal solution to sub problems. For instance, what kind of solution to a problem? Making choice out of a number of possibilities, like that road cutting. Making choice out of a number of possibilities. Look what possible choices there can be. Like that road cutting, can be 1, 1, 1, 1, or 1 with 4, or 2 with 2, or 3 with 2, and so on. Then solving one or more subproblem that are the result of a choice. Like that Fibonacci, yeah, that F3 actually from F1 and F2. Save it when you call F5 because F5 is F4 and F3. F3 already did, just save it yeah, for time being. We use solving one. That Fibonacci is actually solving two, yeah, previous one and previous of the previous. Solving one or more subproblem that are the result of that choice. This the choice. Yeah. Characterize the space of subproblem. Like if Fibonacci, you have this. Let's say this F3. It means this F2 plus F1. So that solution to subproblems must themselves be optimal. For the whole solution to be optimal, use cut and paste argument. Okay, so I'll show you this. Yeah. Sorry, I like to have an offline class, yeah, but I can be seen last week. I come and first class only one, only 1% is really worthless. That I travel 400 kilometers by motorcycle because I like to ride. Yeah. And only one person coming. You know. Of course, I really appreciate him so much. Then second class, how many? Five students. Yeah. Then tomorrow it is six, and then the next one nothing. Yeah. So totally, so I have 12 students of four class divided by four. I mean three in general. So I will inshallah back to campus when everything back to normal. Totally not is better like this, yeah, because I know you guys also maybe want to go to campus, but your parent is allow. No, 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 son, no daughter. I don't like it. I'm worried about because many viruses, not just COVID, maybe something else. Okay, cut and paste. Yeah, what is cut and paste? Yeah, let's say now. Yeah, I mean the current situation. I have the question I already in F4. What F4 mean? F4 it mean I already have F3 and F2 yeah. So I save it this F3 and F2 yeah. And then when this F4, if I then okay, see that current situation now this yeah. Okay, let's say this one. And then I already move to the next process. It means I already in the second situation. In if F5. Okay, F5 yeah. F5 mean F4 and F3. Then okay, no I cut this. Cut because I save it yeah. That memoization. You save some space. I cut it yeah. And then I paste. Yeah, I paste. Okay, I cut and paste because it is very stupid if I redo the F3 process because I already did in here, right? I did it here. Just paste it. Yeah. Okay, I paste it in there. Okay, right? Okay, and then F4 I did before, yeah. Of course, I just use it. It's in F4 I have F3 and F2, right? Then it means the okay the previous one is F3, yeah, F3, the previous one is F3. When I'm in here, yeah, when I'm in that F4, when I in F2, in I and when I at F5, it means my previous one is F4, so it means I save it, and the previous is F3. Okay, just use it then, and so on, yeah. So F4 that I already did, yeah, I can cut and paste. It is exactly the same, yeah, exactly the same process. But don't like say, for instance, yeah, the number is let's say 20. Yeah, why don't just instead of calling that process, why don't just use that 20 yeah, to be calculated? Yeah, by select the F6. Yes, it's finished. Yeah, if metric that Q, yeah, easy like to done this. Yeah, yeah. Show that solution to sub problems must themselves be optimal. Yes. For instance, that Fibonacci, back to Fibonacci again. Okay, this yeah. Okay. The very beginning. Yeah. F1 should be optimal. Yes, it is the only one. Of course, should be optimal. F0, of course, optimal is only one. Yeah, this is what this is 0. This is one, the number. So this the sub problem optimal. This is only one. I mean, you cannot compare. And then rejoin on the student. Calculate in F2 ya become one. Okay. And then if you come to F3 ya, of course F1 only one ya, only one. It means one. Of course, it's optimal. And then F2 because from the optimal one and zero, so should be also optimal. So it will become two. Yeah, you can show that that sub solution, sub problem have the sub solution too. Sub problem this. So sub problem must themselves be optimal, yeah, for the whole solution, for the original solutions to be optimal. Cut and paste argument, right? Just like I did just now, yeah. That if and so on, yeah, then I give you if F4, then F3 just cut because it is really optimal. Use it. Yeah, you don't need to calculate. Yeah, let's say this F3, let's say 7. Yeah, just use the 7 number. Okay. Okay, then okay, so this is number one. Yeah, we need to show optimal substructure that you have some how to say. Yes, it is combinatorial. Yes, but also like you have kind of fundamental how to say like a smaller process, yeah, under you to make you bigger, make you optimal substructure. Number two, write recurrence. Okay, back the book. Yeah. This recursive define the value of an optimal. Yeah, this I mean, if recursive, I mean recurrent. Remember we have recurrence. Yeah, we have only three methods yeah, to check about the recurrence. Which one? Which one? Which one? Yeah, remember that time. Write recurrence for the value of an optimal solution. Kind of the value of an optimal solution. Question this. M optimal equal to minimum of overall choices k sum of M optimal of all subproblem resulting from choice k plus the cost associated with making the choice of k. In the how to say that metric yeah this also Wenten metric this yeah. So you need to choose because when you only split by two yeah, of course it's of course only two process yes, but in where this like in the center AB plus CD yeah. Or wait, it mean if you divide by two, it mean you save the number of process yes only two yeah, only twice. A time B plus not plus. I mean the process yes yeah, plus the time C time D. Then we can combine. So the result of A multiple by B need to calculate, need to multiply by the result of C times D by D. I mean only twice, only two yeah. Then thinking, oh, it is the biggest one. It thinks the how to say the optimal one. No, yeah, see the 41,200. Then actually I divide by three, yeah, BC first, and then the result of BC time D, and then that result time A three times, yeah. But remember, it is three times, but actually the result, yeah, actually the cost is the optimal one. This is also three, but it's not necessarily AB first, and then C and D. I mean the division of that this. Okay. Then 1, 2, 3 or 2 and so on yeah. Okay, so this depends. That's why this also can need to take into account yeah the cost. This the cost the cost shaded with making the choices of k like this. If you are in here yeah like I said, or you are in here, or you are in here yeah, it's k. So that the number of different instances of subproblem is bounded by polynomial. And then you can check like that before yeah. It was exponential yeah, and then at the end of the day actually it is n power 3 after you carefully uh, analysis that metric, because anyway it is only first calculation. And then this, remember, yeah, you cannot once again multiple by wrong way, guy. You only can multiple by that adjacent one. Yeah. But which one? Yeah, which one need to calculate first? That is the problem. Yeah. And it is not random. Yeah, it's like arbitrary. It is two. Yeah, recurrence. The recursive can, if you can show that it is recursively define the value. And then number three, of course, only to compute, calculate the value of an optimal solution in a bottom-up fashion. Yeah, this like that. Fibonacci. Yeah, this. So that you always have the necessary sub-result pre-computed or use memoization. It's actually similar idea, yeah. I mean, pre-computed, it mean you also save. Sorry, yeah, actually also save, yeah, save to that temporary storage. Yeah. But memoization also. Yeah. Actually, I don't know. I'm not. I don't see the big difference between sub-result pre-computed and memoization. And memoization like to save space. You are sacrificing some space to save that value, because it is better to sacrifice some space than you redo that process. It means, remember, always time as our considerant. Number one is time. Time. Because time cannot be folded. Time cannot be shrink. Space, yes, yeah, you can use whatever. Okay. Mm-hmm. Compute the value of an optimal solution in a bottom-up fashion so that you always have the necessary sub-result pre-computed. That mean before, yeah, I mean the thing is, if you are in here, yeah, so before you are already calculate and save it. But memoization is also similar actually, yeah. Yeah. Okay, just click. Mm-hmm. 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 Simple mutually recursive descent parsing. Berarti to cache, like cache. Memoization refers to a specific case of this optimization, distinguishing it from form of caching such as buffering replacement. Mm-hmm. Tabling, ya, kalau maksud tabling. Mm-hmm. Okay. 1968 memorandum to be remember. Remember the result corresponding subset. Mm-hmm. Yeah, actually similar, yeah. I mean, pre-computed or memoization. Well, actually, I mean, similar idea for me. Yeah? And then, okay. So this is actually correct, yeah, to get, remember what? Value, the value of the optimal solution already can be obtained until the tree. I think, because as human being, yeah, if we can make use, utilize, yeah. See if it is possible, yeah, to reduce the space requirement by forgetting solution to sub-problem that will not be used anymore. Okay, I mean, three, and then it is to reduce the space requirement, yeah, forgetting solution to sub-problem that will not be used anymore. If you see that Fibonacci, yeah, you can see that that space. For instance, if you were the F6, yeah, why we were the about F4, F3, for instance, yeah, I need F5 and only F4. Yeah, if I store it in F6, then this space can be discarded. Yeah. Who care about this? Yeah, that is correct. I mean, if you can see whether you can save that space. Okay. So if it is possible to reduce the space requirements, therefore getting solution to sub problem that will not be used anymore. Yeah, for the F6, yeah, and then F5 and F4, F3, F2, F1, care about that. Yeah. Okay, so actually this is still this. Sorry, this not still not like one part. And then this is the value. If then you want to see, or to say that the way you cut that value, yeah, then this. construct an optimal solution from computed information, which record a sequence of choices made that lead to an optimal solution. The record is the how to say the note of sequence of choices. Oh, I choose this first, and then this. Cuma the process. Yeah. Process also very important in here because maybe from this process you got inspired, you got utilized, okay, that the sequence of the choices made. Yeah. And then the last one, it is LCS. Yeah. It is actually very useful, for instance, to combat the COVID-19. You need to find, and for instance, that vaccine. Yeah, vaccine. The thing is, vaccine. There is two things. Yeah, that you learn from the vaccine itself. This vaccine have two things, like the weakened vaccine or the dead vaccine. Yeah, the one is totally different with not particular item from vaccine itself. For instance, it's only DNA of that spike, yeah, for that COVID-19. But anyway, in order to be able, yeah, to recognize, because the vaccine is when it been put in our body, yeah, and then the real vaccine coming, then our our antibody, because already learned, yeah, from that vaccine, then can recognize. How to recognize? To find the pattern, right? To find the pattern. And then this is, if you get, for instance, the longest common subsequent, okay, I have like 10, and then let's say this is 15. Of course, we don't need to make it all match, yeah, but only in some multiple thing. Let's say if let's say yeah, 70% of that virus I can recognize, and this, yeah, the longest common subsequent can be, let's say, 70%. Okay, so this virus, okay, just attack it. This is very good in bioinformatics, actually, the LCS, longest common subsequent. Okay, let's say two text string are given, let's say X and Y. And there is a need to quantify how similar they are. Yeah, like this is this is so slow. I mistakenly click. This is not preferred. Yeah. Let's say X is the virus. V. Y is antibody. That antibody. I mean, after we got vaccine, and then that antibody, that Y. That's why antibody will always, so X coming. Yeah. And Y try to recognize X, right? Need to quantify how similar they are. Let's say that 70%. Okay, this virus, attack it. Oh, only 30%. No, it is not virus. Similar with virus. Okay, just let it be. It is our friend. Yeah, let's something like this. Yeah. See, comparing, yeah, DNA sequences in studies of evolution of different species. Spell checkers. Yeah, so the spell checkers, when we are like grammar checking, spell checking. That's the most important. Oh, this is the example. This COVID-19, yeah, battle. So for the virus, it is it's better to prevent. Yeah, this was a vaccine to prevent. Also, the other one also can be that you, how to say, cure the virus. Similar. Yeah. Always the same, that we need to find which one, because sometimes, like for instance, the HIV, HIV virus, the virus who responsible for AIDS. They actually usually they hide up in the core of the cell. So that's why antibody cannot recognize. They are very smart. They're very smart. So the, let's say, the feature of HIV virus actually is not so strong like this. No, actually very smart is that able to hide itself, in that core of that cell, and then of course replicate, producing all the time. Remember, somebody died not because AIDS itself, just because the immune system and then weaken. Then actually the other disease, yeah, make it die, but not the AIDS itself. But the feature of that AIDS is very good in hiding up core of the cell. So if you can recognize, yeah, by this comparing DNA sequence. Remember, virus is, somebody said, this is not living being because there is no reproduction, something. It is only DNA notice the group of DNA, yeah, but they can replicate by using other cell. I mean, that host cell, like a human being or that bat, yeah, or that monkey and so on. But in order to combating that virus, not just COVID-19, we need to do so-called DNA sequencing to see which or similar, for instance. Yeah? And this LCS is a very interesting topic in bioinformatics. Yeah. So one of the measures of similarity is the length of longest common subsequent. Longer, better. Yeah. 7. But then I have 120 of 150. I compare. Oh, this is virus. 7, no. For instance. Okay, definition. Z is subsequent of X. So X it mean bigger, yeah. And then Z something like this, for instance, this. Or maybe in here Z. If it is possible to generate Z by skipping some, possibly none, characters from X. For example, this. X is ACGGTA. ACGGTTA. Y is CGTAT. So LCS, longest common sequence of XY equal to this. That is correct or not? CGTAT. I can get this C, G, T, and then A. Because the thing is, I can, oh, the CG, yeah, I have CG in here, right? So it is easy to see CG. Okay. And then for T, I get also T here, this also here. And then I skip T in this. Skip this, yeah. And then I have A. Okay. So T and A, yeah, wasn't TA. Yes. Then for this T, I skip it. So yes, correct, yeah. CG, TAT. Then if I skip T, and then I calculate this, yeah, CGTA. If I what's that? Skip not skip, yeah, not skip T, and okay, CGTT. Okay, yeah. Again, yeah, once again. Okay, for that. So if I got CGTA here, yeah, I got this, yeah. So CG this, and then TA. CGT, CGTT this. So actually I got CG again, and then TT. Then if I got also CG, CGT, yeah, and then I skip A, yeah, to get T, also CGTT. Okay, so it is correct CGT or CGTT. In 4, yeah, in either case. Okay. So to solve LCS problem, we have to find skips. Yeah. Skips, which one? Like I not skip, like TT, or I skip the second T to get A. Yeah. So have to find skips that generate LCS XY from X, and skip also that generate LCS XY from Y. Then which one? Yeah. So what kind of skip in X? What kind of skip in Y? And then that step, yeah, to distinguish between in a particular problem it is can be solved by DP or not, yeah. And we need to show that it has an optimal substructure. We make C to be empty and proceed from the ends of XM. So N, I mean from right, this and go on. So of course it Z, yeah, empty first, yeah. I mean there is no C or G or D or what. It is very funny actually, yeah, that DNA, yeah, only CGTE, yeah. It's actually our Kudo is so, yeah, of course it's omnipotent, yeah. DNA, yeah, is guanine and so on, yeah. Cytosine, guanine, was it? It's only have this adenine, guanine, thymine, and this cytosine. So cytosine, adenine, guanine, and thymine. Only 4, but the combination of these, wow, yeah, make us human being or animal. Let's say we are in monkey actually. 99 or 97% share the same, yeah, but that 3% or 1% different, we are totally different. Yeah, okay. So this is very interesting in bioinformatics, really. If you guys are really interesting, so you'll see so many method, yeah, to sequence of the DNA sequencing. Yeah, so okay, yeah, C should be 0, 1, and then gradually, yeah, you will collect it which one, yeah, collecting which one is the longest. Okay, make C to be empty and proceed from ends of XM. I mean this, yeah, from right, X1, X2 until XM, and YN. I mean YN this, the right. If XM equal to YN, append this symbol to the beginning of Z. So actually from from back, yeah, from back, and then you put in Z. If it is equal, append this symbol to the beginning of Z and find optimally posisi, yeah, this, let's say G and then T and then A and then let's say T, yeah. You're gonna read from right, of course easy. I mean it doesn't matter, it doesn't matter. Anyway, as long as it is equal to both of them, yeah, xm or yn, it means yes, it is share. It doesn't matter actually, yeah. You read from left or right, it doesn't matter. The thing is, it is this common section. It means both x and y um, has that particular element, so it doesn't matter actually, yeah, left or right. You are reading this um, sequence, yeah. Okay. Yeah, if x and xm equal to yn, append this symbol to the beginning of C and find optimally LCS of then no m minus 1 and yn minus 1. So the rest is, so there's the rest. If not the same, how to do if not the same? If the same, just put append, I mean add up. If not the same, this skip either a letter from x, this you skip it, skip from x, or a letter from y or from here, you skip it. And decide which decision to do by comparing LCS XM yn minus 1 and LCS XM minus 1 yn. Then you can compare this XM, previous one, yeah, with yn minus 1, or the previous of the previous of x, yeah, XM minus 1 with yn. Okay, yeah. This makes sense, yeah. This one, yeah, XM yn minus 1 or LCS XM minus 1. Okay, it means the yeah, that before, yeah, that before x before, this is y before, so this is y, the previous y, this is the previous x. Then cut and paste, remember that Fibonacci, cut and paste argument. Okay, recurrence, yeah, the it's most important, that the recurrent in LCS, because we look, yeah, this is actually only number 1, yeah, remember, to find or to show that a particular problem has optimal substructure. Second one, you need to show that they have recurrent or recursively suboptimal. The algorithm could be easily extended by allowing more editing operation in addition to copying and skipping. Copying and skipping. The thing is, you can actually edit. I mean, if copying, just it is the same, yeah. Skipping, you skip. But maybe also editing, it means you allow something in between. Edit, editing. It means this, changing a letter. So like T, okay, it is okay to change to become A, then and become eligible to be add up and to be append. For instance, yeah, they become A. Changing letter, okay. Let Cij, LCS, Xj, Xi, Yj. If Cij, if I equal to 0 or j equals to, of course, the 0. Nothing to be compared, yeah, if I or j 0. But if I comma j greater than 0, and then the same, it means you append, yeah, the same. That's why Cij becomes Cij, Ci minus 1, j minus 1 plus 1. Because we count, yeah, longest, I mean, Okay, I got one. Okay, one, and then another one. Okay, I got this the same. Okay, two. Oh, actually 10. Totally 10. The 10 particular element who what can be obtained, yeah, from X and Y, for instance. Yeah, that's why we need to add up one. I minus one, J minus one plus one. I mean, is that increasing? This increasing. And then if it's not the same, xi not equal with yj xi, then you push the maximum of this cij minus 1, comma, like this, yeah. Which one you wanna skip, yeah? This cij minus 1 or ci minus 1, comma j. And then sub condition in the problem restrict subproblem. What is the total number of subproblem? Condition in the problem restrict subproblem. Okay, yeah. Because when we have these two, yeah, then you just actually, what to say, you can like this, yeah, go from left or to the right, yeah, this. Then you observe which one is, how to say, have the common, yeah, between these two. You can hear that pseudo code. This is initialization for I, okay, 0, for J 0, and okay, this M, and this is another N, and then check, yeah, if it is, yeah, this is plus, yeah, it is the same. If it is the same, then C I minus 1, J minus 1 plus 1, then you put in there. And then you have another, how to say, array bij, and then you say copy. I copy it because it is the same. If not the same, it is greater than. It means need to skip x. Likewise, skip y. Okay. Then you can write by yourself, guys. CGDAT. Then I said we have CGDA, and then CGDT. How much we can reduce our space requirement if we do not need to reconstruct LCS? Okay. You can try, best that from that Fibonacci, yeah, Fibonacci, very easy to um, imagine, yeah. And then we also have merge sort. I mean, actually, in the beginning, we have merge sort, yeah? Merge sort, and then Fibonacci, and then we have LCS, but it's similar, yeah. Can be forward that metric, yeah, metric multiplication. So it is why this is similar, yeah. Or to reduce, for instance, yeah. I just put, yeah. Okay, so that's it, yeah. Any question, guys? Or you still have many things to do? Okay, yeah. This stop, yeah. If no question, stop. No. Just thinking about the midterm, yeah. As usual, if our TA have no idea, I also have no idea. I just use the previous one, yeah. I mean, APL easy. Okay. Okay. If no question or no comment, I will stop now, yeah. Thank you for your attention, guys. Please keep healthy and keep happy, yeah? And then, inshallah, we can meet, yeah. But really, I will back to campus if really back to normal because they're like last week and there's only one or two or three or four, and it's not worth it, yeah. Your parents also worry, my parents, my family also worry. Yeah? Okay, thank you guys so much. Wish you have a nice day, yeah. Okay, assalamualaikum and good afternoon, guys. Thank you so much. See you guys.
Thank you, sir.
Thank
Good
you, sir.
afternoon.
Thank you,
Welcome.
sir.
Thank you, sir.
Yes. Thank you, guys. See you guys. Thank you.
Thank you, sir.